students, welcome to next class, that is your sixth class. Okay, so today we'll go for the continuation of the ionic conduction in NaCl. So in the previous class we have seen how this sodium chloride conduction takes place. Okay, and today we will go for some of the extension part of this conduction. Okay, so you can take a graph of this log of sigma. Okay, that is temperature per ohms per centimeter versus you can take inverse 1000 k t. Okay, and small you can see here, small like this, something like that. Okay, and your dotted line you can take it here, extrapolated, and like this, like this. Okay, so this is your first, this is your second, this you can take it as first and dash, first, second, and this you can take it as third. Okay, so like this you can take it, and here something you can take 1.2, 1.4, 1.5, 4 bar, 3 bar, 2 bar, 1 bar, like this. Okay, so now here what you see, this is the ionic conductivity of pure NaCl, ionic conductivity of pure NaCl. Okay, as a function of, as function of reciprocal of temperature, as a function of reciprocal of temperature. Okay, so this graph is nothing but the conduction, ionic conductivity of pure NaCl as a function of reciprocal of temperature. Okay, now here you can see state 1, state 1, state 2, 1 dash, and state 3. Okay, so here stage is I can say this is first stage. Okay, the stage 1 and 2 here second stage. Okay, so stage 1 and 2. Okay, so they correspond to intrinsic and extrinsics, they correspond to intrinsic and extrinsic regions. Okay, now here dash line here, so dash line extrapolation here like this, then here it is extrapolated this way. Okay, okay, this is divergent here like this, so this is extrapolated here. So this dash line they represent extrapolation. Okay, the dash line represents extrapolation, extrapolated line. Okay, of the region 1 and 2 where the deviation occurs. Okay, you can see here deviation is occurring here like this, it is coming here, it is deviated like that. Okay, where deviation is occur, and here stage 1 dash here, this one, this stage 1 dash I will write here, the stage 1 dash. Okay, so this occurs very close to melting point, this occurs very close to melting point of your NaCl. Okay, so that is your 802 degrees centigrade. So, and has been attributed to two possible can say cases. Okay, here, and the first you can see the anion becomes the anion becomes increasing. Okay, increasing in the first cases. Okay, two possible causes are there. So in this graph, so first causes I can write here, the anion becomes increasing mobile, first one, anions become increasing, which act as a mobile. Okay, and make more contribution to sigma, so and make more contribution to sigma anion. So remember here, so anion becomes here more attributed to two possibilities, and they are the first possibilities that Cl minus anions becomes more increasingly, and mobility of that as contributed to the increase in the sigma here. And the second case, the second possibility is long range d by Huckel's interaction. Okay, long range d by Huckel interaction, long range d by Huckel interaction between cation and anion, between cation and anion. Okay, between cation and anion vacancies, between cation and anion vacancies. Okay, so this become appreciable at high vacancy concentration and at high temperature. Okay, high vacancy concentration and at high temperature. Vacancy is always creation at the high temperature. Okay, now here vacancy formation is easier, and here in this case in sodium chloride vacancy formation is easier. Okay, vacancy formation is easier, and the sigma is increasing, and the sigma value increases, that is conduction increases, sigma value increases. Okay, below 390 degrees centigrade, below 390 degrees centigrade, okay, below 390 degrees centigrade, so sigma deviates from the ideal. So you can see here the sigma deviates from the ideal. So below 390 degrees centigrade sigma deviates. Okay, sigma deviates from the ideal. Okay, and from the ideal extrinsic lines, whatever the extrinsic line should be here, second one, so it deviates from the ideality. See here, so it deviates from the ideality. Actually this is a dotted line here, it should come this way, but deviates from the ideality at 390 degrees centigrade. Sigma deviates from its ideal extrinsic line, that is extrinsic line, from its ideal extrinsic line, that is the third. Okay, 3 I have shown here in the figure. This is attributed to the formation of defect complexes. This is because of the formation of defect complexes. Okay, so defect complexes. Okay, for example cation vacancy anion vacancy pair, like cation anion vacancy pair. Okay, this is a, or cation vacancy aliovalent impurity pair, cation vacancy and aliovalent impurity pair, impurity pair. So these are the cases. Okay, so there is deviation. And the activation energy of stage 3, if you see the activation energy of this stage 3 here, okay, here the activation energy, okay, if you see the activation energy, okay, so here the activation energy is greater than the EM, is greater in this third stage. The activation energy, that is EM, what we explained in the previous video, is greater. Okay, EM is greater than, you can see, to the stage 2. Okay, so this is what we have to think in the sigma is greater than the stage 2. I will write here stage 2. Okay, if you consider the stage 3, the activation energy is more as compared to, greater than as compared to the stage 2. So that's why it is difficult to be make the quantitative measurement. So it becomes very difficult for the NaCl to make quantitative measurement, measurement. Okay, so it becomes very difficult to make the quantitative measurement of effect of dislocation, effect of dislocation, effect of dislocation on sigma. Okay, because the number cannot be controlled, because whatever happening here, vacancy is creation, and this one, the number cannot be controlled here. Okay, that is what. And here the extrinsic conductivity of NaCl, I will write extrinsic conductivity of NaCl, okay, is controlled by the aliovalent doping, controlled by the aliovalent doping. Okay, so the effect of impurity on sigma is used to study. Okay, the effect of impurity on sigma value is used to study, since their number can be controlled and and measured. Okay, by a formula, and have more effect to the sigma in extrinsic region by using a formula K is equal to molar concentration of vacancy of Na plus into vacancy created by Cl minus divided by molar concentration of Na into molar concentration of Cl. Okay, so this is what. Okay, so where this is what, this is the equation for the concentration of Schottky defect, SCHOT, Schottky defect, concentration of a Schottky defect equilibrium. K means what? Equilibrium. Okay, so here at equilibrium given by, so this law of mass action, given by the 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 law of mass action. Okay, so this is what. And K is unaffected here, so whatever the K value is there, it is unaffected. Okay, it is unaffected by small amount of, unaffected by small amount of aliovalent impurity, aliovalent impurity. Affected is a small amount of aliovalent impurity. Okay, and that and the denominator whatever we have seen is equal to 1. So what happens now? So it becomes that vacancy of Na plus into vacancy of Cl minus, okay, will be equal to constant, will be equal to constant, because the denominator factor of Na and Cl becomes 1. So this becomes equal to constant now, okay, is equal to 1. So that means where you can see which is, we can give it as a x naught, okay, whole square. Okay, so where in intrinsic region, in intrinsic, if you see, where in this, according to this, in intrinsic region, okay, what will be the intrinsic region? X naught will be equal to, so that of vacancy of Na plus will be equal to concentration of vacancy of Cl minus. Okay, so this will be equal. That means if the number of cation vacancy, if the number of cation vacancy in extrinsic region is increased, okay, if the number of cation vacancy in extrinsic region increased, okay, what will happen if this vacancy in extrinsic region is increased by adding some equivalent cation, okay, by impurities, by adding some equivalent impurities cation, okay, what will happen? Then the number of anion vacancy decreases, obviously, because it is equal to constant. The number of anion will decreased. See here, the number of anion will, but that remains to be constant here. That's why this will decrease. If you increase this by adding equivalent cation, this will decrease. Okay, not all impurities. So that is what it is very important to study the defect, the conduction in the NaCl here. Okay, it's not so easy. Now if you see here, if you are, not all impurities lead to such increase in sigma. So if you, it doesn't mean that all the impurities will increase the sigma value, conduction value in extrinsic region. Okay, some impurity of some like monovalent, that K plus or Br minus, such type of impurities. Okay, if you add this in NaCl, what will happen now? They has a little effect on sigma. So such impurities has a little effect on the sigma value. The sigma means conduction value. Okay, effect. Okay, unless it is present in very large. So otherwise you have to put very large amount in this one. Then only it will affect the sigma. Otherwise it will not affect the sigma value. Okay, this also you have to keep in the mind. Okay, impurities that reduce concentration of mobile species. Okay, so whatever these impurities, sometimes what will happen, they reduce. Sometimes the impurity reduce. Okay, the concentration of the mobile species. Okay, and they result in reduction of the sigma value. They result in this, instead of increasing the sigma value conduction, they drops, the sigma value drops. So addition of impurity also is very much important. Not that all impurities you add and it will increase the sigma value. Sometimes it will decrease the sigma value also, and sometimes such type of monovalent type of impurities may not have any effect on sigma unless you put in major quantity. Okay, so this is also you can keep in the mind. Okay, and sometimes it will reduce definitely if divalent anion, like divalent anion, I will write here divalent anion, if you want to add. Okay, divalent anion, usually they are not soluble in NaCl, but that is not going to give more effect on the sigma value. Okay, so concentration of less mobile anion vacancy, that will sometimes would increase the more mobile cation vacancy. Okay, so that also happens here, the concentration of less mobile, because anion means what, they are less mobile. Okay, so if less mobile, so if you increase the concentration of the less mobile anion vacancy, so that will increase. Okay, so that will increase the more mobile cation vacancy, that will increase the more mobile cation vacancies. Okay, so this also is to be remembered. So whenever any divalent anion, dissolves in NaCl, so what will happen, the concentration of less mobile anion, okay, the concentration of this less mobile anion vacancy would increase the it would increase, this will increase, that would increase the more mobile cation vacancy. But sometimes this is a solubility problem will be there. That's why this effect is not seen much more in this NaCl, but for AgCl, so this is prominent. Okay, anion is a prominent impurity to note down the changes in AgCl. So I think this is more than sufficient, this one for the ionic conduction in the alkali halides. Okay, now we'll go for next, that is your AgCl. One more they will ask, silver. Okay, so this silver, not AgCl, that is your silver chloride conduction. So this is also called as interstitial conduction. Okay, interstitial conduction, because here predominant defect in AgCl is cation Frankel defect. You know that cation Frankel defect. Okay, so this is a predominant defect in the AgCl. Okay, cation Frankel defect here, that is interstitial Ag plus ion, that is interstitial Ag plus ions. Okay, interstitial Ag plus ions associated with associated with the interstitial Ag plus ion associated with the Ag plus ion vacancy. Ag plus ion vacancy associated to Ag plus ion vacancies. Okay, now here the interstitial Ag plus ions are more mobile, so this thing you have to keep here in this. Interstitial Ag plus ions are more mobile here. Okay, this is the thing you have to keep in the mind. Then the Ag plus vacancies, then the Ag plus vacancies. Okay, then the Ag plus vacancies. Okay, now here two possible mechanism we can show in this, two possible mechanism. Okay, so we can show here of the of this AgCl conduction here. Now here for the migration of interstitial Ag plus can be shown here. Now you can take it here, AgCl, AgCl, Cl, AgCl, Ag, AgCl, AgCl, Cl, Ag, Cl, Ag, and here one interstitial Ag is there here. Okay, either this is a one mechanism 1 and 2 I can write here. Either this Ag can transfer into this interstitial stage and help for conduction, or this Ag I will write here, one more Ag I will take it here like this. Okay, now this may hit here directly like this may hit here. Okay, Cl. Okay, so Cl, Ag, Ag, Cl, Ag. Now here what happens, either it may go here, that is directly from interstitial side to another interstitial side, or sometimes from here it will knock this this Ag. Okay, in turn this will knock here like this. Okay, and this vacant whatever is created will be occupied by here like this. Okay, so this also can be shown. So in the cubic stage we can show in this way also. Okay, so this way also you can show here. So here we can take it as your Ag here, so where we can, it is very good to knock out here. So here also Ag, here Cl, then here Ag, here Cl, Cl, Ag, Cl, okay, Ag, some like this. Okay, AgCl you can draw it here. Now here it is knocking here. Okay, so interstitial here Ag is there. Okay, so this will knock at this Ag here. Okay, here not this one, interstitial, this will knock here and this will go in different direction. Okay, like this, either this direction movement will be there like this. Okay, this is from the interstitial Ag when it knocks here, so you can see here, so it may diverge here. So this is a B. Okay, this type of this also you can show here. Interstitial can knocking the edge here. Okay, not this one, this is one of the edge no doubt, but here interstitial is like this, interstitial in middle of this window this will knock out this edge Ag. Okay, so that we can say that here the pathway for the migration of Ag plus by interstitial mechanism, by interstitial mechanism. This type of, this is called as interstitial this one, the interstitial mechanism hitting this one and creating vacancy here. Indirectly it hits and this is created vacancy and this will take place here. Okay, so that we call it as an interstitial. So here I will write here, two are there, the first one is here, so Ag plus going to here this. Okay, so what is called migration of interstitial, I will write here first one, there is migration of interstitial, Ag plus ions. Okay, Ag plus ions. Okay, one by direct interstitial jump. Okay, this is called direct method, direct interstitial jump from one interstitial to another interstitial, direct interstitial jump. This I can take it as a one, direct interstitial jump. Here this is 2, I will take this as a 2 where it is knocking. So second one is what? So second one I can write it here, that indirect interstitial indirect interstitial mechanism. interstitialcy mechanism. Indirect interstitialcy, INTRSTITIALCY, interstitialcy mechanism. Okay, so here the migration of interstitial G plus ion of here direct here, and one more is interstitialcy mechanism. Okay, so these are the two cases of the I can say the mechanism here of AgCl. Okay, so here, so you can see that that the second whatever we have seen the cube, so that is also called as knock-on process. Okay, that is second one, whatever that is your knock-on process. Okay, so where in the cube you can see that it is knocking one of the Ag plus, and this Ag plus can go in different direction. Okay, that we call it as a, that second figure we call as knock-on process. This also sometimes we call it. Okay, so and you can see in the first diagram that an interstitial Ag plus ion jumps to adjacent empty site. Okay, and another we can see that indirect what happened, the interstitialcy mechanism is going to happen, and that we call as a knock-on process. Okay, so here the interstitial Ag plus causes here Ag plus causes. Okay, because here what happens, it is surrounded by 4 Ag plus neighbors, and it moves off and it move off it, so that's why of its metal, and that's why these are responsible for the mechanism here, for the conduction mechanism. Okay, now yes, and that movement in the adjacent interstitial site, and we have seen that itself occupies the vacant lattice here, and but it depends now. It becomes very difficult now. Okay, so whatever we have seen here, two mechanisms, it becomes very difficult. Okay, how to know this, whether this mechanism is occurring by the interstitial site or by interstitial movement side, or by interstitial C, that is knock-on process. How to know this knock-on process or movement into interstitial side? Okay, it becomes very difficult. Okay, and to distinguish this between direct and indirect, how to distinguish between direct and indirect mechanism? Okay, so to distinguish this mechanism, diffusion and conductivity data analysis is done. Diffusion and conductivity conductivity data analysis is done here. Okay, so in diffusion what is happening, the crystal is doped with radioactive Ag plus. Okay, in diffusion what we do, so here the crystal is doped with radioactive Ag plus, Ag plus. Okay, so this we do, and their migration is followed. So wherever in the during this conduction, wherever it migrates, that is followed. Okay, because it is been doped with a radioactive element. So this is what diffusion. Okay, we see. And in conductivity, all Ag plus, in conductivity what we are doing in this, all Ag plus including this doped, all Ag plus. Okay, ions, not only the radioactive ones but all ions, their contribution to the conductivity is measured. Their contribution to the conductivity is measured, and according to Nernst-Einstein relation, according to NER-NST, Nernst-Einstein, okay, relation of self diffusion or diffusion coefficient for self diffusion, d to the conductivity, diffusion versus conductivity. Okay, it is given by the formula that d is equal to kT by Fn Ze square into sigma. So this is the formula, Nernst-Einstein formula, which correlates diffusion versus conductivity by this formula. Okay, so where Ze is the charge on the mobile ions, this is a charge on mobile ions, Ze, charge of the mobile ions. Okay, and N is their concentration, okay, how much mobile ions are there, and F is a correlation factor. Here F is nothing but your correlation factor. Okay, and this depends on Heaven's ratio. Okay, so this is what Heaven's ratio, where the value depends on the ion migration. Okay, and the Heaven ratio value depends on the ion migration. Okay, so since diffusion measurements determines the movement of the ions themselves. Okay, and conductivity measurements overall charge displacement. Okay, the Heaven ratio, whatever the Heaven ratio we have obtained here for two different mechanisms, that is diffusion as well as conductivity, whatever the Heaven ratio we are getting here, so it has been found experimentally, experimentally that the interstitial mechanism, okay, from this Evans ratio, it has found that the interstitial C mechanism is the predominant here. Okay, it is going to occur. Okay, mechanism is operative in AgCl. This is a final. Okay, according from the Evans ratio, from this formula, it has been obtained from the study of the radioactive Ag plus and of the radioactive Ag plus ion by diffusion and all ions conductivity by conducting method, that from the Evans ratio value, it experimentally it has been proved that interstitial C mechanism is operative in AgCl. Okay, not interstitial. Okay, that is knock-on process. That is very much important. This mechanism is for conduction is main here in AgCl. Okay, so this is what about the main thing you have to explain in the examination, that conduction in AgCl. Okay, so this is one. Here both NaCl and AgCl. So if you see both here NaCl and AgCl has rock on process. Okay, has the rock salt structure. Okay, rock salt structure. So in vacancy mechanism, Na plus moves from one corner of the cube via interstitial side in NaCl. Okay, but in AgCl the interstitial mechanism, knocking mechanism occurs. So that is a difference. Okay, from the which displace the corner side. Okay, so this is what going to happen. Okay, so I think in this video this is more sufficient. So today we have completed our important NaCl conductivity with one graphical presentation, and we have completed our AgCl conductivity which is having two mechanisms. Okay, one interstitial and interstitial C, that is knock-on process. Okay, in the next video we will see some of the graphical methods of this AgCl, as well as the effect of again here impurities. Okay, if you add aliovalent impurities and its effect in the AgCl. So how we have learned effect in the NaCl, similarly the effect of impurities we will learn in the AgCl in the next video. Thank you.